All right, talk a little bit about surface finish characterization. So because of the layered nature of the process, the surface finish changes as a function of angle because you have a step of each layer that comes out, and that step inherently increases the roughness. What you're looking at on the bottom here is what we call our gauge block. It's kind of a standard piece that we throw around to give people an idea of the surface finish, the texturing, the morphology of the surface. And you're looking at sort of the bottom facing surfaces where, again, 90 degrees is a vertical orientation and down to 10 degrees off a horizontal. And what you see in the graph here is a measurement of roughness. We're using SA in this case. SA is the aerial analog to RA, which is a linear profile. This is done on a Keyence 3D scanning microscope to gather this data. You can see near vertical is where we achieve our minimum roughness, right? And it gets down below about 4 micron SA. And again, for reference, SA usually measures very closely to RA, if not a little bit higher. But as you sweep down an angle and you get down towards our minimum printable angle, the roughness increases. And so depending on what your roughness requirements are, if they fall somewhere in between the sort of min and max, you may want to work on orienting your part slightly differently to optimize for the angle of your most critical surfaces on your part. Okay, so I'm going to get into angle guidelines. And this is a commonly referred to term in Metal AM. And like I mentioned before, the sort of common rule of thumb is for most materials and most processes that are making fully dense material, everything below about 45 or 40-ish degrees below or above horizontal needs to have support structures and able to maintain surface finish and to not warp and ultimately fail to print. And the reason for this, or some of the factors that determine what that exact value might be, are things like obviously the angle itself, the curvature of the leading edge, and I'm going to give some simple geometric examples that explain that. The number of layers that you have to propagate this. So in some cases, you'll see that, well, a certain feature you may be able to print for a certain number of layers, but if you try to propagate it much farther, then eventually the stresses accumulate to enough of a degree that it'll fail the part. Laser angle of incidence, and we've worked and what I mean is the angle that the laser is hitting it relative to the leading edge growth direction of the geometry. And our VELO3D processes have been tuned to mitigate most of any of these effects and other local geometric effects. So, of course, the distortion and warp breakdown is a function of thermal stresses, which are related to thermal gradients during the solidification process, and all this is related to, if there's differences in how the thermal energy is being sunk back into the part, then the parts the different geometries are going to behave differently. And so again, I'm talking about breakdown here, right? And so the plots I'm showing over the next handful of slides will use probability of breakdown. So low meaning you're very safe of not having surface finish breakdowns or having excessive warp. Moderate meaning this is getting into a dangerous case, and it depends on some of these other subtle effects that I've mentioned over to the left. And high meaning you'll almost certainly have issues printing this without supports again, of course. So I'll use a plot that shows for a given geometry the angle normal to the surface, 90 being vertical, 0 being horizontal, and the height that it has to propagate, or how many layers you're trying to propagate this particular geometry. Okay, move into the first couple cases. Start with something very simple, a plane. And I'll kind of bookend this with two different cases. One is an unconstrained plane, where you're building off a base plate that I'm showing transparent here. There's no walls on the outside, so you're left with the sharp corner. If you cut this in X, Y, and watch the layer printed, you're going to have a 90-degree angle there. And then a constrained plane. And for reference and for this, let's assume that this is about a 1-inch span between these two vertical walls. And so it's fairly well constrained. And what you'll see on the plots is the area that we'll call moderate probability of breakdown, where you run some significant risk, has more of a restriction on the unconstrained plane. And this is mostly due because of how the thermal behavior is behaving differently for the skin process, the downskin process, than it is in the middle. And so the first parts that will warp and distort are these edges. And you'll see that for the constrained case, where the walls are acting almost as a support structure, if you want to think about it like that. It keeps everything more tidy and more constrained, and that yellow area here disappears and it shoves over, and so you have more safe area when you're talking about printing really low angles like the 10 and 20 and 30 degree ranges. To use this in a real example, I'm showing a part from a company called KW Micropower. This is a turbine diffuser. It's about 10 inches in diameter. It's a titanium part, and they were bidding this part out to a number of manufacturers and getting no bids from almost everybody. And the reason being mostly because, kind of a sidebar, it's very difficult to print large titanium parts without cracking because of the brittleness of the printed titanium. And VELO has a proprietary process to mitigate some of that, print large parts like this. But focusing mostly on the geometry, what you've got here is, if you look on the left, all these are intake ports for some sort of impeller, and that put a fluid in and turn it around at kind of a sweeping pattern. And if you see this, call this upside down, more or less. You have the entrances in the middle, but the exits on the outside, and they sweep at very low angles, talking about down to 10 degrees or even less in some cases. And so when you approach looking at these really low angles, you can think about this kind of like a constrained plane. You've got a rectangular profile, and so you've got a planar surface that's changing and sweeping through angle, but it behaves like a plane at any point in time. It behaves like a constrained plane because you have these veins separating the ports. And so we can go back and think about the constrained plane rule, and that if you get down into these areas that are down to 10 degrees or so, they're safe because of how this part is constrained. Okay, getting into the next general example. I like to use cones as a simple analog for curved surfaces. And I speak about them usually in two classes. One is kind of outward growing conical surface, or a convex surface, for example on the top. And the other one is inward growing. And these two behave very differently. I'll get into some examples of where this really applies after the slide. You can see that by these graphs, the outward growing cone or convex structure is one of the most difficult geometries to print. The reason for this is, if you think back to kind of the first graphic I showed, you think about printing a new layer on top of this cone, and this bulk fill inside here that's being applied is shrinking and trying to peel these things up, kind of like a potato chip, sort of warping the edges up because it's shrinking that top layer. On top of that, you have a secondary low angle surface here, or skin surface that's being applied. That's basically melting a ring, solidifying, and it's warping in a similar, with a similar vector, that being, it's warping kind of in and up. And those two sort of stress vectors work together to make a leading edge that really wants to warp up. And so your minimum angle that you can print safely is higher in a lot of cases. I mean, it really depends on how long you propagate this, because the stress accumulates over many layers. Conversely to that, if you look at a concave surface, you got something that behaves quite a bit differently. And what happens here is, you can think about it again in the two main stressors. You think about, now this is kind of split, and you have a bulk fill that's shrinking and trying to warp this edge up, this inner low, shallow overhang edge up. But you've got a skin process that's going to run in a ring around this that is in roughly the opposite direction. The stress vector is roughly opposite. It's trying to contract and shrink it and pull it inward here. And so those two they sort of deadlock each other into a really stable surface. And so an inward growing curved or conical surface is one of the most stable geometries to print. And so the rules here are quite a bit different, and apply much differently. So you can print a cone as large as you want, full height, or the full build volume is as large as you can fit, down to 10 degrees without any issue in general. So typically you're not looking to 3D print something just to print a cone, right? It's a bit more complicated than that. So let's look at a real example. Let's use this simple shrouded impeller as an example. For the sake of argument, let's ignore the outer surfaces that aren't quite as critical, that can be touched up, machined, whatever, more easily. Let's concentrate on the most critical features here, which are the inner flow paths. And so in this inner flow path, the risky surface in this orientation is going to be this down-facing surface. And if you think about kind of back to our curvature rules, when this prints up layer after layer in Z height, you've got basically an outward growing cone. Now it's different because it has some constraints here that actually help it a little bit, but it's in general an outward growing cone. And if you go back to that graph I showed for an outward growing cone, you run the risk at lower angles of failing much more easily. And so you think about the angles of this down-facing surface and realize that this is this is probably getting down to about 10 to 15 degrees off horizontal. The outward growing conical shape is not very safe down there for very long. And so you're going to want to try to consider a different orientation, or if necessary, having to add supports. But if we quite simply flip this thing upside down from the previous orientation, now you've got this down-facing surface that is at the same angle, because we've just flipped it 180 degrees, more or less. The profiles are similar. But that forms roughly an inward growing cone on this surface. And this inward growing or concave structure is very stable. And so these 10 degree, 15 degree, and then sweeping out and up are actually quite safe. It kind of runs a line something like this, if you want to think about how it's printing. You keep yourself in this green area. And this geometry is perfectly printable without supports on the VELO system. And we get a lot of these examples. Here's a beautiful example from a company called Hanwha. It's a shrouded impeller. This thing's pretty large. It's about 11 inches in diameter. It's made of nickel alloy. It's using power generation. And they wanted to have really tight tolerance machine surface for a lot of the outer ones. And that wasn't a problem because the machining is pretty standard. But they really wanted the solution that was optimized for the inner flow paths. And on other systems, a lot of these, again, think about everything below about 45 degrees or 40 degrees is going to have to be full of supports. The removal is very difficult. And then post-processing, to get those surfaces back to being acceptable is much, much greater. And so it makes much more difficult business case for this. So Hanwha settled on using the VELO3D Sapphire system for this, and it came out with a great result. And I encourage any of you to go on our website. You'll see a white paper that was written independently from the contract manufacturer that owns the Sapphire system and Hanwha, a representative from Hanwha. And they do a very thorough analysis of this part. So I encourage you to take a look at that. Okay, last rule here. I mentioned briefly free-floating parts. And this is a big difference from some of the systems. And when I say free-floating, I mean that it's not connected to the build plate. It doesn't have any support structures that are connected to the build plate. You don't have to add extra material around it or very, very close to it to help control it. You simply have to follow a couple of rules I'll go over, and you can reach in as soon as this thing's done and pull it right out of the powder bed because it's floating loose in the powder bed. The only real rules are that to print a floating geometry, it has to start from a small cross-sectional area, or roughly a point, and it can only start from a single point. So if you look at the graphic on the bottom left, you have this kind of arch shape. If it starts at a point, very small cross-section, no problem, and it can grow out into any other geometry, and it behaves all the other rules that we've gone over. However, if it starts at 2 points, the issue here is that each of the points will start fine. You'll propagate out of those points fine, but when these two independent free-floating bodies meet each other up here at this connection, the stress from the residual stress from the process up here is going to kick these out and distort these because they have no attachment to a build plate and they're not supported. So you kind of think of like if you're printing a V shape, it's fine. If you print a W, you get yourself in trouble when the two independent bodies connect. An example of this used is this turbine blade I'm showing on the right. And this was rocked back on its corner, printed free floating. And the advantage here for these types of parts that you can print in this orientation are that you don't have to finish a build plate. You don't have the cost of cutting the part off the plate. And you have the freedom to orient these parts anywhere, not only in a kind of a single layer section in X, Y, but you can stack them very cleverly in Z height as well. That means you can get more parts and print it at a higher density of fill per layer, which increases the economics of the print. And you can make much larger prints that don't have touch time in between. So you can print for weeks maybe instead of a day because you're printing many layers that you stacked on top of each other. And so for parts like this, there are great potential business cases to save a lot of money with this technology. And again, the reason why you're able to do this on a Sapphire is that the loose floating part in the powder is not moved at all with the recoater. With other systems, you have a subtle push when you plow the powder over. Okay, so that's it for the rules. One thing I want to mention quickly is that VELO is constantly innovating. And so we're taking all the numbers that we've kind of gone over today and continually pushing them out into more applications, making it more generalized. And so coming soon, you're going to see a lot of the low angle numbers change with kind of increased capability and stability. We're going to take a lot of the thin features that we've done and better generalize them. And interactions between extremely thin features and larger features are a bit difficult to generalize, and we're working that into certainly applications like the heat exchanger that you saw in the previous slides. And we're continually expanding our material space. And so now that we've gotten into nickel-based, titanium-based, and aluminum-based alloys, it's relatively easy to expand in those metal bases. And one important note about these improvements is these are simple print preparation software upgrades because they're just process changes. They're changes of the laser commands. So it means that you don't need to upgrade any of the hardware on the system. The system doesn't run differently. There's not a next generation system that you have to buy to get this technology. And all this license is included with the purchase of the system. So if you're nervous that we don't have a certain capability today that we're working on, but we will tomorrow, that you don't want to buy the machine until tomorrow, well, it's going to come, and it's going to come to all the customers, and it's going to be rolled out essentially for no additional charge on top of the purchase of the system. So real high level, just to go over some of the keynotes. VELO3D is doing with its advanced process control, advanced metrology and hardware control is enabling geometries that couldn't be printed before, or that didn't make sense from a business case standpoint to print before. It offers material that's fully dense out of the system, better than cast, and on par with the best of the laser powder bed systems that are out there. It reduces the need for support and the associated post-processing with the support structures, and will improve business cases for parts that are already being printed. And in general, if you're in the early stages up front, it allows for much better flexibility in design because of the much fewer constraints, the design guideline constraints that are put on metal AM parts today. So I hope this sheds some light on it, and we're going to open to some Q&A now, but I encourage anyone who's interested in talking about parts on a high level and capability on a high level and wants to get more information about that, or wants to look at specific parts, to please reach out. As Mike mentioned, that's what myself and my team does all day long and are happy to do to help be transparent, work through any issues that you have, and help find out if VELO3D and the Sapphire system are good for your application.